Alright, in this video I'm going to talk about how to make the Lewis structures for some covalent molecules. I'm going to go through a list of steps here, but it makes sense as I'm going through them to give an example so you see what I'm talking about. So these are the examples I'm going to work through in this video. SO2, CO2, CO, and CO3 2-. And then when we're done, I'm not going to go through everything. So for example, formal charge, we typically leave that consideration until grade 12. So for the purposes of this, I probably won't go all the way through formal charge, but maybe I'll make another video to talk about that later. But anyways, here we go. Okay, so first of all, pick the central atom. To pick the central atom, if there's one of like sulfur and two oxygens, then obviously the sulfur goes in the middle. But if it's not that clear, the general rule is, if we imagine the staircase in the periodic table that represents the metalloids, the closer an atom is to that staircase, the more likely it is to be the central atom. So atoms that tend to be the central atom are things like carbon and silicon and sulfur and phosphorus and nitrogen in that group in there. So here we have sulfur. That's our central atom. Put the other atoms around it. So I'll put an oxygen here and an oxygen here. This isn't going to get the shape right, but it'll just get us in the right direction. Add one covalent bond between the central atom and the other atom. So doom, done. Okay. Octet all atoms except hydrogen. So by octet, I mean put in 8 valence electrons. We might not leave it like this, but you just put them in. Now, does everybody have 8? Keeping in mind that these sticks represent 2. So 2, 4, 6, 8, 2, 4, 6, 8. 2, 4, 6, 8. Everybody's good. Okay. Count the number of electrons available to the molecule. So here, what we're doing is we're considering the number of each kind of atom as well as the number of valence electrons it has available to contribute to the atom. So sulfur has 6, and oxygen has 6, and there are 2 oxygens. So we get 6 plus 2 times 6, which is 12. Which makes the whole thing 18. Now, compare the number of electrons on your diagram. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so currently my diagram has 20, and my predicted, or the number I should have to work with, is 18. Let me just count that again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yep, okay. So we have a problem. So the way we can reduce the number of electrons on this is to... So the way we can handle this is by taking away some of these electrons and replacing them with a double bond. So those guys are gone, and by replacing them with this double bond, we can see that we've maintained the octet around each atom while replacing 4 electrons by 2 and overall reducing our number. So we made a double bond between this sulfur and this oxygen. It was an arbitrary choice. I could have done it on the other side. I just grabbed that one for no good reason. Now we're going to recount and decide if we want to make any more double or triple bonds. We always make more double bonds before we make triple bonds, but I don't even think that'll be an issue in this case. 2, 4, 6, 8, 10, 12, 14, 6, 2, 4, 6, 8, 10, 12, 14, 16. One more time. 2, 4, 6, 8, 10, 12, 14, 16, 18. Good, that's right. So now my diagram has 18 electrons as predicted by my number. And so we can see that we have found the Lewis structure for sulfur dioxide, and we can stop. So that's that's our first example. Let's go ahead and erase that, and then we'll go ahead and do our next example. In these next examples here, I'm going to move a little bit faster. CO2. So C is our central, because there's one of them in comparison to the two O's. I'm going to put in one bond around each. So central atom, put one bond around each. Now I'm going to octet all of the atoms except hydrogen. No hydrogen, so octet everybody. Now I'm going to count the number of electrons that I should have in the molecule by considering the number of valence electrons from all the molecule's constituents. Carbon has 4, oxygen has 6, so since I have 1 carbon and 2 oxygens, I can see that I have 12 plus 4, 16 electrons available for this molecule. Now let's go to the diagram and see, based on the initial prediction, how many electrons I'm actually using. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I currently have 20 in the molecule. So I'm going to have to make some double bonds here. I'm going to just arbitrarily do it on the left-hand side first this time, no good reason. So I take out 4, add 2. Now I can recount. 2, 4, 6, 8, 10, 12, 14, 16, 18. So now I have 18. I'm still too high. So again, instead of making a triple bond, this time it's not an arbitrary choice. This time I'm going to go to this side and make another double bond. And then I'll recount again. 2, 4, 6, 8, 10, 12, 14, 16. And now my number that I need and my number in my diagram agree. And so I have my Lewis structure. Let's do the next example then. Carbon monoxide. No central atom here, we just put 1 carbon, 1 oxygen, put a bond between them, and then octet them. I've got to, using their number of valence electrons, predict how many I should have to work with. Carbon is in the 4th column. Oxygen is in the 6th column, so they have 4 and 6 electrons to work with total for 10 electrons. Let's go to the diagram and see how we're doing here. 2, 4, 6, 8, 10, 12, 14. Okay, so I'm currently at 14. So that's too many. So I have to make some double bonds. There's 1 double bond. 2, 4, 6, 8, 10, 12. So I'm reduced to 12, but it's still not enough. I need to get down to 10. So this is just an example of a molecule where there's nowhere else to go with the double bond, so we make a triple bond. 2, 4, 6, 8, 10. Now we're at 10. 10 looks like 10, and so that's the Lewis structure for carbon monoxide. One more example here. This one is a polyatomic ion. This is a group of atoms that bond together covalently and have a charge left over once they've done that. We're going to do CO3. And we'll see how that charge affects the number of electrons that we have available for the molecule. 1 carbon and 3 oxygens, so obviously carbon has to go in the middle. Putting in a single bond for each, and then octetting the oxygens. Now, carbon contributes 4, each oxygen contributes 6, and then the 2 minus charge tells me that I have 2 more electrons than I expected that I would have in the first place. So for this molecule, I would have 4 plus 3 times 6 plus 2 more than I thought I was going to have based on the charge of 2 minus on this polyatomic. So that gets me 24 electrons. Oops, I nearly made a mistake here. Notice that I did not octet the central carbon. That's a common mistake that students make as well. When you octet them all, make sure you octet the central atom as well. Okay, let's count our electrons now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. See, if I had missed octetting that central carbon, then I would have thought I had the right number, and I would have missed the fact that I do need to form a double bond with this molecule. just going to do it with the top oxygen. That's an arbitrary choice there. I put the double bond in there. I could have put it anywhere else, but now I can recount 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now I have my right number of electrons. That's the Lewis structure for this. Because it has a charge, we do a separate little thing here where we put it in big square brackets, and we put the charge outside the big square brackets, and that's how we represent having a charge. So those are some examples of Lewis structures for covalent molecules. There's a little bit more to it in formal charge. Some of them are a little more ambiguous about where you should make the double bond or how you should make the double bond. We'll address that later, but for now that should get you through most of the common covalent molecules.